Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the conference. Oil refining optimization. Oil refineries. Structure. A simplified flowsheet of a crude oil refinery is shown in the graph. The process is divided into 3 stages: crude oil management, crude to fuel transformation, and blending operations. To describe the structure of a refinery, HI has selected the ISA 95 standard, which allows easy sharing of information with other systems, and/or mathematical models that share this standard. The image presents an example of a refinery, which is composed of 5 facilities, or process units. And industrial services plant, where the transformation of energy sources is carried out, to meet the different forms of energy required by the process plant. Connectivity between the 2 processes is based on the consumption of auxiliary services, directly and/or indirectly, carried out by the units to carry out the processes, that allow the transformation of raw materials into refined products, consumption that is a function of the so-called level of activity of the units. The processing of ancillary services can be conceived primarily as a process of transformation of the energy required by industrial processes. The following diagram summarizes what has been said. A refinery is the union of 2 processes: product processing, conversion of crude oil and biomass into refined products by means of process units, and auxiliary services transformation, processing of ancillary services required by processing units by means of special units, called service units. Units are represented based on the products they consume as inputs and those they produce as outputs. The units are interconnected with each other, in such a way that they form a chain, in which the outputs of some units are inputs of others, until they reach the storage tanks for dispatch of products to the consumption centers. The process units are physical facilities where the transformation processes of the products are carried out. In addition to the material inputs required by the units, they also require auxiliary services to carry out the production process. As a result, useful products and unwanted waste products, contaminants, are obtained, which must be controlled to ensure the quality of the environment. As crudes are of different characteristics, refineries must adapt for each of these types, and that is why a refinery can use different processing processes than other refineries. In addition to the difference in crude oil, the economic and technical factors also influence the type of refinery. Despite these differences, in general terms, refinery processes are divided into separation, conversion and product treatment or finishing processes. In addition to these so-called primary, or basic processes, there are others such as petrochemicals and secondaries. The graph presents a general diagram of what a crude refinery can be, which can be summarized as the connectivity of a set of process units, of different types, that work together to produce the refined petroleum products demanded by the market. The type of technological processes that are carried out in the process units, that make up the refinery are presented in the table. A biorefinery is a structure that integrates biomass conversion processes, organic matter of animal or vegetable origin, and equipment to produce fuels, energy and products. Under the generic name of biomass, a very heterogeneous set of materials is included. Both by its origin and by its nature, it is possible to differentiate it in natural biomass, that produced by wild ecosystems such as algae, green plants and forest products. Residual biomass, that which can be extracted from agricultural and forestry residues, and human activities. Agricultural, livestock and forestry activities, as well as agri-food and wood processing industries, generate a series of residues, and byproducts, that are usable as biomass to obtain energy. This is also known as lignocellulosic biomass. The concept of biorefinery is analogous to that of oil refinery, where multiple fuels and products are produced from petroleum. The fuels that can be obtained from biomass are summarized in the table. The image presents an example of a to produce sugarcane ethanol biorefinery, which is composed of 6 process units. Biofuels in their specific processing maintain differences in the type of technological conversion, but for modeling purposes it can be characterized as a multifunctional biorefinery where all types of biofuels are produced: bioethanol, biomethanol, biodiesel, hydrogen, biogas, biogasoline, as well as several biochemicals, plastics, ammonia, paints, solvents, resins, fertilizers, from different types of biomass. The table presents the description of the basic chemical processes included in the graph. Linear optimization model for sales and operations planning, S&OP. High oil ref includes a generic model that can serve interchangeably to plan, at the aggregate level, the 2 crude and/or biomass refining processes. The level of aggregation is fundamentally related to the non-linearities associated with this type of process, but not with the level of detail with which it is possible to represent the production processes, which can be spatially detailed in all units used in the production of refined products. High oil ref considers the refining process as a union of 2 processes: product transformation, conversion of crude oil and biomass into refined products, through process units, and energy transformation, processing of auxiliary industrial services required by process units, and which are consumers, and/or energy producers, in so-called service units. The objective of optimization is to determine the production plan that meets the demand for refined products, according to an offer of available crude strips, purchased or to buy, during the planning period. From the point of view of mathematical modeling, high oil ref considers 2 types of process units. Rigid unit considers a unit as a process that is defined based on certain input, raw material, refined final or intermediate products, and that produces refined products in fixed proportions, and flexible unit considers multiple possibilities for production processes in which the proportions of the blending of the products consumed, and the quantities produced, are determined by the model. For flexible units, quality specifications must be introduced as part of the model constraints, so that the volume and/or weight product generated by the model meets these specifications. High oil ref includes a multi-technology unit, associated with the multiple ways how the process unit can operate over time. By this way, the model can select which technology, mode of operation, it uses as a decision variable. This possibility implies that in strategic and/or tactical models the process is described based on the amount, or percentage, of time during which each of the available technologies is used. In scheduling models, binary variables are required to describe which technology is used at each instant, or period of the planning horizon. The modeling of the connectivity between production units can be done in an aggregated way, through tanks, or in detail through collectors. This representation is appropriate when it wants to visualize bottlenecks in the flow of products, and when it wants to link the auxiliary service plant with the process plant. Modeling a refinery based on a single type of unit has its drawbacks. A fixed refinery always produces excessive amounts of some finished products, a flexible one generally has too much flexibility compared to a real refinery. That is why the best strategy to model refineries is based on a competition between rigid and flexible units considering costs, demand, capacity, production, profit, and possible expansion of the refinery. However, the units, rigid or flexible, can operate continuously, or in batches. In addition, the flexibility of the unit extends, not only to the different refined products but also to the different raw materials, to the sources of the raw materials or even to any possible combination of them. In this way, the refinery processes can be optimized through a model with a unified mathematical representation, where all types of units, processes, and forms of operation are incorporated. As a byproduct of processes are considered the pollutants of the environment, on which restrictions may be imposed. Linear optimization model. Mathematical formulation. Based on the above, a model of the refining process is proposed, that allows describing a refinery composed of multiple multi-technology units, rigid or flexible, differentiating each type of unit with its own equations. To unify the modeling around a common production reference, all units will be associated with the concept of activity level of the unit technology, which must be defined based on the quantity produced of one of the outputs of the unit, presumably the most representative resulting product. Connectivity between units occurs through collectors that link them. This detailed connectivity is part of the detailed models, and it is ignored in the aggregate model. In both models, intermediate compensation tanks are ignored, which are considered not to provide information in strategic, or tactical, models such as those being formulated. The indexes that represent the entities involved in the refining sector model are B type of biomass, C type of crude oil, D type of refining/derivative, E technical specification/quality, I collector, refinery, A auxiliary service, T time, U process unit, and X technology. The following discusses the constraints that are part of the model. Production capacity. The processing capacity is calculated based on the length of the planning period T, from a nominal daily capacity. This calculation process is typical of strategic and tactical models, but differs in the case of operating models, in which binary variables are used to assign the entire output of a period to a technology or mode of production. Additionally, the restriction of time allocation to technologies must be met. Rigid units. In rigid units, fixed input-output coefficients are assumed, and modeled based on the activity level of the unit. In this case, technical or quality specifications are not considered, since it is assumed that the established mixture meets the specifications. The equation is similar for the amount of final products and byproducts consumed, and/or produced. Flexible units. In flexible units, the proportion of the mixture is determined in the optimization process. In this case, quality restrictions are incorporated that the mixture must satisfy. The model presented has as a hypothesis a unit that consumes multiple types of crude oil, or biomass, and that produces a main product, on which the technical specifications are established, or quality, that must meet said product. The remaining products and/or byproducts are established proportionally, based on the amount of main product that is produced, that matches the activity level of the unit. Then, activity level unit equal to production main product in the unit. The theory supporting flexible mixtures is presented below. The first hypothesis is that the technical specification, or quality, of the final product is a function of the mixture. In this case, a linear function is always valid, which is achieved through the contributions to the specification of the different components, raw materials, that participate in the mixture. Contributions to the specification are proportional to the component's share in the mixture, measured as the ratio of the weight, or volume, of that component to the weight, or volume, of the final product. In the case of specifications based on weight, we have specification is equal to the summation over K components of the contribution K multiplied by weight K divided by total weight of the product. The specification, to comply with a range of validity, is lower limit less or equal than specification less or equal tan upper limit. The above condition appears to be nonlinear since the weight, or volume, of the component is a decision variable. However, multiplying the two sides by the divisor gives a linear constraint. Therefore, the above conditions can be written for the specifications, in terms of the participation of the components in the volume or in the weight, as 0 is less or equal than the summation over K components of the contribution K minus, lower limit multiplied by the volume K. The process of forming technical specifications can be interpreted as each raw material contributing a differential quantity of technical specification to meet the total required, which must meet the ranges defined for each specification. To relax the assumption of linearity about the specification, you can use a piecewise linearized function. If the function has diminishing returns, diseconomies of scale, the problem will be convex, otherwise binary variables will be required to guarantee the representativeness of the approximation. The above expressions correspond to the constraints that must be included in the optimization models to ensure compliance with the specifications, a condition for each specification which is associated with the subscript E. Flexible units. This implies the following set of equations. The first defines the activity level of the flexible unit based on the production of the main product. Based on this, it is possible to formulate two equations, one for volume, and another for weight. A similar equation can be formulated for biomass process units. Discriminating when each lower and/or upper limit should be applied, through the QPLU and QPU, U, sets, for weight specifications and QVLU and QVU, U, for volume specifications, the above conditions can be expressed for crude oil processing units as show the table. And for biomass processing units we have similar equations. Operational variables. The operational variables refer to the existing variations in the technology, in the different units according to the technical specification of biomass or crude. An example is the units that process products which tend to depend intrinsically on the technical specification of the crude oil, or biomass, such as vacuum distillation, or atmospheric distillation columns. In this case, the technical specifications of the crude oil or biomass vary affecting the unit. In other types of units and technologies that do not depend on the technical specification of the crude oil or biomass, they operate at a constant value. These variables can affect the quantities of both consumption and production of products, and/or byproducts in a unit, as well as the cost of operating the unit, according to the conditions under which the refinery operates, and its deviation from how it was designed. Balance of matter in collectors. For detailed models, the collectors must satisfy the balance of matter, that indicates that what is received must be equal to what is delivered. Additionally, the capacity restriction of the collector must be considered. Frontier conditions. In addition to the previous ones, for each period the model of the refining sector considers the following restrictions: consumption of Type C crude oil in the refinery RE, biomass B consumption at refinery RE, demand for refined product, environmental requirements D in the refinery RE, and auxiliary resource consumption on unit U. Fractional distillation optimization. It is the activity related to the distillation of petroleum and the crude distillation units CDUs. The hypotheses of linearity of the processes in the refinery are not met, and therefore the exact optimization must consider the nonlinearities of the petrochemical processes. Within these, the description of the behavior of the CDUs is very important, since it is the core of the refining business. This section is based on the document Distillation Blending and Cut Point Temperature Optimization in Scheduling Operations. Crude Distillation Unit, CDU in the oil refineries, final products such as fuels, lubricants, and petrochemicals are produced from crude oil and process units, considering their operations in coordination with tanks, pipelines, mixers, etc. In this process, the full range of hydrocarbon components, crude oil, is transformed, separated, reacted, or blended, into smaller boiling point temperature ranges, resulting in intermediate and final products, in which real-time planning, scheduling and optimization using distillation curves of the streams, can be used to effectively model unit operations, and predict the yields and properties of their output currents. The graph presents the fractional distillation process, which produces all petroleum products. They vary depending on the temperature, at which they are extracted from the distillation tower. To maximize efficiency, effectiveness and economy of mixing, blending, reacting, converting and separating fractionating inside the oil refinery, normally the refinery is formed by a chain of CDUs. Unit operation processing and product blending are integrated by monotone interpolation, to mix and reduce distillation and evaporation temperatures, for petroleum products in an optimization environment. Blending distillation temperatures is well known in simulation, whereby cumulative evaporations at specific temperatures are mixed together, then these data points are used in piecewise cubic spline interpolations to revert back to the distillation temperatures. The graph shows the nonlinear behavior in the extremes of the distillation curves, where increments in the temperature, abscissa, cause a nonlinear increment in the evaporations, ordinate. Hydrocarbon streams, crudes, fuels, petrochemicals, are characterized by distillation curves in terms of their quantity, yield, and quality, properties, and how they vary with respect to temperature. These data are determined by experimental methods using laboratory distillation columns in which hydrocarbon fractions are collected at certain boiling point temperatures, to define their quantity and quality data at each boiling temperature. This data can be used in mathematical models. Since obtaining TBP curve data directly from a laboratory distillation is expensive and time-consuming, the normal procedure for distillate products is to determine distillation curves by applying American Society for Testing and Materials (ASTM) methods such as D86, atmospheric, and D1160, vacuum, or simulated distillation (SD) methods, using gas chromatography (GC), such as D2887 and D7169. Figure shows the ASTM D86 and TBP data from the Colorado School of Mines for a straight-run gasoline stream from a CDU, plotted with volume yield percent as the ordinate. The ASTM D86 and TBP temperatures are near equal at their 50% yield point, whereas D86 yields are underestimated below the 50% yield, and D86 yields are overestimated above the 50% yield. The characterization or testing of hydrocarbon streams of both crude oil and its derivatives is decomposed, divided, or characterized into several temperature shutdowns based on what is known as the true boiling point, TBP, temperature distribution, or distillation curves. These are one-dimensional representations of how quantity, yields, and quality, properties, data of hydrocarbon streams are distributed, or profiled throughout their TBP temperatures, where each cut is also referred to as component, pseudo-component, or hypothetical in-process simulation and optimization technology. If we compare a CDU's crude oil feed distillation curve with all its product distillation curves, it is interesting to see what are known as overlaps between the light and heavy adjacent products. This represents what is referred to as non-sharp or non-ideal fractionation. The difficulty with blending the distillation temperatures from several component materials is that these TBP distillation temperatures do not blend linearly on a mass or volume basis. Mixing indices for distillation temperatures, and for other properties such as cloud point, pour point, viscosity, etc., allow indexed, or transformed, properties to be mixed linearly. The authors propose a technique to optimize the mixing of the distillation curves of various streams, by adjusting the shear temperatures of the distilled streams, in effect, their initial boiling point, IBP, and final boiling point, FBP, to manipulate their TBP curves in offline, or online environments. By changing or adjusting the front end, and back end of the TBP curve, for one or more distillate blending streams, it allows for better control, and optimization of the quantity, and quality of final product demand, allowing for better maneuvering closer to and around downstream bottlenecks, such as tight property specifications and volatile time and demand flow constraints. This displacement or adjustment of the IBP and FBP of the TBP curve requires that the unit operation has sufficient handles, or controls, to allow this type of cutoff point variation, where the solution of this higher-level optimization would provide set points to advance lower-level process control systems, which are now common in oil refineries. When yields, evaporations or relative distilled quantities are used as a function of temperature, IBP, TO1, and FBP, T99, can be manipulated, for example, to adjust or shift the distillation curve by interpolation and/or extrapolation, to increase or decrease the front end and back end of the curves. The marginal adjustment can also be compared to the fine-tuning of the distillation curve, and this will ultimately result in the change of all relative yield values, along the total, or general, TBP temperature range of the distillate stream. This will have the desired effect that we can alter the amounts of evaporation in the downstream mixture to better control and optimize the mixing quantity and quality specifications to meet market demands. However, when we handle TO1 and or T99 for any distillate component flow, these values, interconverted to DO1 and D99 if necessary, must be sent as set points to an appropriate advanced process control strategy in the operation of the respective unit. These strategies are available for analyzers that can be linked to pump heat exchangers and temperature controls to achieve the desired increase and or decrease in initial and final cutoff point temperatures. Considering that the example is a straight-run gasoline, its old IBP, OTO1, and FBP, OT99, are 91 and 230 Fahrenheit degrees as seen actual figure. If in an optimization problem the new IBP, NTO1, and FBP, NT99, change to 85 and 214 Fahrenheit degrees, respectively, we expect a hydrocarbon amount increase in the front end, lighter fraction, and decrease in the back end, heavier fraction, of the distillation curve, which means that the front end of the gasoline in the optimized problem receives heavier hydrocarbon fractions from its lighter adjacent neighbor, and the back end is reduced, giving material to its heavier adjacent neighbor, both with respect to the extrapolation in the initial, front end, and final, back end, of the distillation curve. The steps of mixing distillates and optimizing the cutoff temperature by monotonous interpolation are: first, move from faster and less expensive experimental methods, such as ASTM-D86, to slower and more expensive TBP temperatures, using well-established interconversion analytical expressions. Second, these interconverted TBP temperatures are converted into pseudo-component-like cumulative evaporations in process design simulators using monotone interpolation, linearly mixed by mass or volume, then converted back to TBP temperatures using another monotone interpolation. If necessary, these values are converted back to ASTM-D86. Third, adjust or move the front end and or back end of one or more of the component TBP distillation curves, optimizing the TO1, 1%, and or T99, 99%, cutoff temperatures, while respecting the relative yields of the adjusted or displaced distillation curves. Significant economic benefits can be achieved by implementing such an algorithm, especially for ultra-low sulfur fuels, that always require accurate prediction of key evaporation points in the distillation curves of the final product. Multi-period refinery planning mixed nonlinear model. This section is supported in the paper. Refinery production planning, multi-period MIMP with nonlinear CDU model. The configuration, like the one shown, it provides information on the major separation, conversion, and blending units, along with the refinery feed streams, product streams, and interconnections between the different units, where the crude is separated into different cuts in the crude distillation unit, CDU. Each cut is sent to a different conversion or treatment unit, reformer, catalytic cracking, or hydrotreatment units, or to product blending. Refineries differ in the number or types of process units they have, depending on the quality of crude oils they process and the product slates. In addition to the configuration, the following information is assumed to be given. Crude oils. The availability of crudes is specified, along with their properties and compositions, usually in the form of crude oil trials. Various processing parameters, property values, and indexes are generated. Refinery units. Capacities of these units, and minimum power requirements. The coefficients required for the yield and property calculations are generated from the units and crude oil information. Product slates. List of products produced by the refinery and their possible constituent streams. The qualities of the product are specified along with requirements, minimum and or maximum. Demands are specified at the end of each period. Product inventory. Initial inventory of the products at the start of period 1. Changeovers. The variations in crude qualities are sequence dependent. The changeovers are specified in terms of duration and cost. Based on the above information, the objective is to determine the operation that maximizes profit in terms of the following decisions for each period: what crude oil to process, the quantities of these crude oils to process, the sequence of processing them, the rate of processing those crude oils and the processing duration, and the refinery products produced, their quantities, and storage requirement. The mathematical formulation for the multi-period refinery planning model builds on the previous work of Alatas, Grossman, and Pillow Rivera, 2011, and Erderick Dogan and Grossman, 2008. The formulation can be broken into 3 layers. The inner layer is the fractionation index model, phi, which is the nonlinear CDU model. The middle layer is the refinery planning model, which in this work is a linear model. The last layer is the multi-period extension, which is a MIMP model. The appeal of the phi model is that it is crude independent. Phi values are characteristics of CDUs, they are readily calculated and updated based on refinery data. It is based on simple nonlinear modeling approach, avoiding more complex ones, calculates cut point temperatures that helps in other calculations and models, and has relatively few equations to add to the planning model. The NLP model for the CDU starts with a mass balance around each unit J, and component I. Every unit yields the top product PD feeding the next unit, and the bottom product PB, which is the product crude cut. The splits of the distributed components are calculated using the phi parameters. For each unit, there are two phi values, one for the rectifying section and another for the stripping section. Choice of the correct value is based on the calculated temperature and the component. The rectifying phi, FR, is used if the temperature is greater than the component boiling temperature, otherwise, the stripping phi, FES, is used. The disjunction represents the phi choice where y is the vector of binary decision variable, gamma is a placeholder for the phi value, TBI is the component boiling point, and TJCRT is the cut point temperature in period T. The component distribution at each unit J is based on the light key LKJ, and heavy key HKJ components for each unit based on the initial and end boiling points relative to each cut. The components lighter than the light key are only obtained in the top product stream, while the ones heavier than the heavy key are only obtained in the bottom product stream. The next model is the refinery planning model. This includes the set of equations for calculating the product yields from each process unit, except the CDU, as well as stream properties calculations, and product blending. Typically, the planning model will include checking the feedstock availability, meeting the product demands and the objective function. However, these constraints and equations are moved to the next layer of the model as part of the extension from single period to multi-period horizon. The throughput of process unit K is calculated using a coefficient multiplied by the feed unit, to obtain the output unit product flow. The capacity requirement of unit K is ensured by using the appropriate constraints. The interconnections between the process units are managed using several splitters and mixers. The crude processing rate is linked to the CDU model. Blending is a mixing unit, but is distinguished by the final product flows, according to the defined constituent flows, and the quality are checked against the product specification, using constraints for the maximum and/or minimum specifications. In this case, the refinery planning model is a linear model. The multi-period layer is based on the approach proposed by Eradirk Dogan and Grossman, 2008. The idea is to determine the length of the processing times for each crude oil, and to use traveling salesman constraints, to determine the sequence for processing crude in each period, and identifying the link to break, and connect the sequence to the adjacent periods. The objective is maximizing profit. When there are no sub-cycles in any period, the changeovers are properly accounted for in each period, and any possible crossovers. Otherwise, subtour elimination constraints are added until all sub-cycles are eliminated. Also, since the duration of the changeovers is relatively modest, the model assumes for simplicity that changeovers cannot cross periods. The extension to this case can be easily implemented. The development of these planning models is broken into two categories. LP models, namely fixed yield and swing cuts, like PIMS, and NLP models, including the aggregate model and fractionation index model. In this case the model is MILP. The multi-period refinery planning model. The goal is to maximize profits or minimize costs. The main constraints are performance CDU, phi model, each crude, each period, mass balances, inventories each crude, each period, and sequencing constraints. The binaries decision variables are to assign crude in period T, indicate position of crude in sequence, and indicate where cycle is broken. The continuous variables are flows, inventories, cut temperatures, etc. The Gantt presents the schedule in the distillation unit of the refinery, for a period of 4 weeks. The paper reports results of 4 experiments. The example 1 produces for 4 weeks, 5 crudes, fuel gas, regular gasoline, premium gasoline, heavy distillate, fuel oil, and treated residue. The image shows the economic optimal solution, before and after subcycle illumination. The image shows the feed and processing time information, and product quantities and inventory. Case: Crude oil scheduling and refinery planning. This case is based on the document Crude oil scheduling and refinery planning by Lagrangian relaxation. Both crude oil scheduling and refinery planning are formulated as optimization problems, and are integrated into a single full-space MILP. The integrated formulation is constructed based on the overlap between the CDU charging operations in the scheduling level, and the CDU feeding decisions at the planning level. And MILP priority slot-based continuous time crude oil scheduling formulation, and a multi-period discrete time NLP refinery planning formulation are used. A multi-scale framework has been proposed to integrate different time representations. The mathematical formulation for the full space problem is developed in 3 stages. Multi-period discrete time formulation for refinery planning, RP, maximizing the total NPV. Priority slot-based continuous time formulation for crude oil scheduling, CS, with multi-period extension, minimizing the total crude purchasing cost, and set of linking variables and constraints of crude oil feedstocks between crude oil scheduling and refinery planning, with the objective maximizing the total NPV minus total crude purchasing cost. The custom indicates that the most common position, when formulating a mathematical model, is an integral formulation, full space, which brings together in a single formulation all the equations that define the problem. This corresponds to a top-down approach. In this case, the model could be called Crude Oil Scheduling and Refinery Planning Model. However, considering the evolution of computational power and algorithms, today in ascending formulation, it is indicated that starts from the atoms, that is, from the basic parts of the problem. This corresponds to a bottom-up approach. The case presented is a good example of this approach, dividing the problem into 2 formulations, crude oil scheduling model, and refinery planning model. These formulations are integrated to form the holistic model. The crude oil scheduling model represents the first part of the process. This type of scheduling problem is usually formulated as continuous time models, which facilitates the coordination of activities exactly, at the instant level. The refinery planning model is more oriented to the use of discrete time formulation, since it involves the planning of activity volumes in multiple process units by periods. Proper handling of these 2 formulations is easier under the divide and conquer approach. The graph shows the flow rates in the simplified refinery planning example. The goals of the 2 models are crude oil scheduling. The goal is to schedule crude oil transfer operations, with a certain limit for ship unloading capacity and tank transfer, and refinery planning. The goal is to optimize the amount of crude oil and intermediate flows, with working modes and capacities given for the CDU and the refinery process units, where the total benefit of the final product is maximized. The crude oil scheduling model is a continuous time non-convex MILP model, based on priority slots. Its main features are given vessel arriving and leaving time, tank inventory management, CDU charging continuously through time, and non-overlapping inlet and outlet transferring. The key variable is the binary variable ZIV, that represents the assignment of the V operation to the property slot I. The key constraints are, time decisions in each time slot must have consistency, non-overlapping operations not in same slot, non-overlapping time decisions are ensured by big M type of constraint, nonlinear crude composition constraint, for each slot I, crude C, and outlet operations V, and other mass balance constraints. The objective function is the crude cost. The crude oil scheduling model is a continuous time non-convex MILP model, based on priority slots. Its main features are given vessel arriving and leaving time, tank inventory management, CDU charging continuously through time, and non-overlapping inlet and outlet transferring. The key variable is the binary variable ZIV, that represents the assignment of the V operation to the property slot I. The key constraints are, time decisions in each time slot must have consistency, non-overlapping operations not in same slot, Non-overlapping time decisions are ensured by big M type of constraint, nonlinear crude composition constraint, for each slot I, crude C, and outlet operations V, and other mass balance constraints. The objective function is the crude cost. The integrated problem, full space problem, is a non-convex MILP. The integration process is linking constraint, defined as the equivalency of CDU charging operations and CDU feeding operations. Full space problem, MILP model containing scheduling, planning and linking constraint of CDU feedstock, and multi-dimensional approach, different time representations. Coordinate planning and scheduling starting and ending times. The design of the refinery configuration is based on the figure. 3 raw materials, associated with 3 vessels, 3 storage tanks, and 3 cargo tanks, are the upstream operations for scheduling. Zone A. In Zone B, there are several process units such as hydrotreaters for light cracked naphtha, LCNHT, coker light naphtha, CLNHT, and diesel, DHT, fluidized catalytic cracking unit, FCCU, delayed coker unit, DCU, stabilizer unit, stabilizer, catalytic reforming unit, CRU, and delayed coker, DCU, are the downstream operations for planning. The distillation unit is composed of 5 towers, a flash distillation tower, flash, 2 distillation units, CDU1 and CDU2, a vacuum distillation unit, VDU, and a debutanizer unit, debut. 3 blenders for gasoline, blender, diesel, blender, and fuel oil, FA blender, are installed in the refinery. Zone C. The graph presents the crude oil scheduling data. The graph presents results for 3 planning scenarios, 12, 24 and 48 days. The graph presents the results of the planning, by groups of 12 days, in 48 days scenario, for the different finished products produced by the refinery. 3 different solutions approaches was studied. Monolithic approach, solve full space model by using state-of-the-art MILP solvers. Hierarchical approach, solving sequentially the 2 sub-problems CS, crude oil scheduling, and RP, refining planning. There are 2 possibilities. The proposed is solve planning, fix CDU feed, and solve scheduling, and Lagrangian decomposition. For the monolithic approach, the different alternative solutions come from the state-of-the-art MILP solvers used. For the hierarchical approach, the sequence of solving the 2 sub-problems CS, crude oil scheduling, and RP, refining planning, is a key decision. Both methods are tested in 3 cases and the computational results are presented in Table 10. The 2 options are stated as scheduling planning and planning scheduling, which explicitly represent the sequence applied for solving CS and RP. The objective value is determined by the sum of the individual CS and RP objectives. This process could be improved if cycles are incorporated to achieve convergence. Which can be considered as a primal dual algorithm that uses an improved subgradient formulation for the dual problem by exploiting a trust region approach. Because of the non-convexity of the problem considered here, strong duality is not guaranteed, and therefore there might be a gap between the global optimal solution and the Lagrangian dual which this algorithm may not be able to reduce to 0. The overall solutions of the 3 cases, 12 days, 24 days, and 48 days, are presented in the table. The objective functions for both monolithic and Lagrangian decomposition approaches are larger than for the hierarchical approach, 75%, 60%, and 6%, for the 12 days, 24 days, and 48 days cases, respectively, corroborating their advantage. Moreover, the proposed LD approach requires less CPU time converging to a small, 1% to 5%, optimality gap, when compared to the monolithic approach using state-of-the-art MILP solvers. The graphs present the computational results of bounds versus iteration number and CPU time. The graphs compare the Lagrangian relaxation method using DICOPT versus the Barron global algorithm. Optimizing the blend of crude oil and petroleum products is a multi-million-dollar application. This section is based on the document Crude Oil Blend Scheduling Optimization, an application with multiple million-dollar benefits. It can be coupled to the production of oil fields, in such a way as to establish optimal plans for production, distribution, export and import. In addition, blending processes extend to petroleum products, for example, lubricants. A case of the optimization of crude oil blend scheduling is presented. The problem involves a pipeline, 2 receiver tanks, 2 cargo tanks and a pipe still. The table presents the batches of crude oil and the receipt and dispatch orders, including the tanks. The Gantt chart presents the crude oil mix schedule for a 10-day planning horizon. The graph shows the trend of the specific gravity cutoff property of whole oil. Reducing quality target variance should be at the top of the list for refinery improvements. Deviations from quality targets should be minimized, to charge the pipe still with a steady mixture of crude oil. Steadier quality crude oil mixtures charging the pipe stills will also translate into steadier operations for downstream production units. It also makes good sense to run pipe stills with a constant flow rate for as long as possible. An example of an improved quality target, or key planning proxy is shown in figure. Hypothetical benefit calculations. Total yearly savings in American dollars, quality target variability improvements such as whole crude oil sulfur, 2 million, reduced chemical injection, 100,000, distressed sale of crude oils from the refinery, 325,000, pipeline penalty charge for changes in sequence or timing, 75,000, spot opportunity for crude oil trades, 250,000, and reduced working capital, 100,000. Total year, 2,850,000. These hypothetical benefit calculations translate into over $2.5 million worth of the potential refinery profit that would not have been achieved with manual scheduling alone. It must be emphasized that this number only provides a benchmark or yardstick Pareto, at least qualitatively, the priorities in terms of choosing between other possible and competing capital investment projects at the refinery. From the perspective of overall crude oil costs of the refinery over 1 year, this $2.85 million in savings is less than 0.41% of the total feedstock cost. Like Herbert Simon, hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.